Yeah, so here's an example of the use of inner product. Example of an application. Of and it's Fourier series. An application of orthonormal bases. Okay, so you recall that we give me a second. Okay, so recall that we were looking at the continuous functions on negative pi pi. So continuous functions. Continuous functions on negative pi pi. And we put an inner product on it. The inner product of fg was 1 over pi, the integral from negative pi pi, f against g. And we saw that this space of functions, or at least we didn't really see this, but we said this, that if we look at the function that's constantly equal to 1 over square root of 2, cosine x, sine x, cosine 2x, sine 2x, etc., then that was actually an orthonormal set. That this was an orthonormal set. Right? That they're all perpendicular to each other, and they're all of norm 1. Okay. In fact, in some sense, and we're not going to talk about what sense, every function in negative pi pi can be represented as some linear combination of these guys, okay, as a naught, some constant times the first guy, plus, some constant times all the other guys, some constants times all the other guys, so k from 1 to infinity. Okay, so you've got a1, you've got some constant times this, and you've got a1 times cosine, a2 times cosine 2x, I'm sorry, a1 times cosine x, a2 times cosine 2x, a3 times cosine 3x, etc. And then bi's on the sine I case, sine I x's. Okay. Okay. So that is to say that in this sense, the set is some sort of orthonormal, some sort of infinite orthonormal basis for the continuous functions. Okay. Okay. Right. So this is something that was actually when it was first proposed in 1798 by Fourier, it was seen as unbelievable. People didn't think that this was possible. That every function, every continuous function, right? It's what is it saying? Right? It's saying that every continuous function on negative pi pi, whatever continuous function you want, can be realized as some sort of combination of, a flat line, right? Here's the flat line, and cosine and sines, cosines and sines. Okay. Right. But in fact, this turned out to be true in some sense, and in many other senses, and this is the mathematics that underlies the compression of sounds, or the digital compression of sounds, or digital compressions of images. At least when I was in college, the TA said that this is the mathematics underlying CD players. When I told this to a recent class, they said, "Oh, Professor, we don't use CD players." But in any case, it's basically descendants of this idea that are used in image compression. For example, JPEG. JPEG compression is based on not this. This is realizing a function as combinations of waves. It's actually based on something called wavelets. There's another course taught at CMC in wavelets if you're interested in that. Okay. In any case, just believe for now that any function, any sound that you have over some fixed time interval can actually be realized as some combination of waves. Okay. And so if somebody gives you a sound, we can figure out the coefficients, right? So given an arbitrary f, right? Think of this as some sound that you've chopped down to live on a particular time interval. We can determine A0, A1, A2, we can determine all the A's and we can determine all the B's, right? Just by using our knowledge of orthonormal sets, right? A0 is of course going to be the inner product of your sound against the function 1 over root 2. AK is going to be the inner product of your function against the cosine kx, right? BK is going to be the inner product of your thing against the sine, right? And there's some way of doing this. Like electronically figuring out what these things are, or mechanically figuring out what these things are. So somebody gives you a sound, and then from that sound you're able to get all these coefficients, or get a finite number of these coefficients, and you don't care past a certain point, because past a certain point the frequency of the sound is beyond human hearing, right? So you chop it off, right? You say, okay, I don't need all of these guys, right? I don't need all of these guys, but I'm going to use some of them, and then I'm going to put those things back together, and hopefully that gives me my sound back in a way that is close to the original sound by my sense of hearing. Okay, and that's so this is a very a ubiquitous application of Fourier analysis. It's all around you. Any sort of compression, right? I'm being compressed right now as I go into this, as I get recorded by this video, right? All the compression is based on this sort of idea. Okay. Okay. Any questions on about this application? It's just for your entertainment, maybe. I am actually teaching a course in Fourier analysis in the spring. However, you can't take it. If you're in this class, then I'm afraid it's the prerequisite for it is 131. So, and this course is a prerequisite for 131. So clearly, clearly you can't take that course.
So like a year and a half from now, we can take it.
That's right. That's right. So you take 131, Although to be honest, at probably a safer route is to go like this, either through Harvey Mudd's discrete mathematics or through Pomona's introduction to analysis, because 131 tends to be a hard course for people. Those of you who are interested in math, these are things that people do after this course. You take some sort of transition course, and then you can take like 131, and then after that you could take this course in Fourier analysis, which will be really cool, I should say, and in the end shows application of the ideas of Fourier analysis to number theory, which you might not expect. Okay. Okay. Okay, so back to orthonormal sets again. We're going to give a small digression into a connection with the method of least squares. Connection with the method of least squares. Okay. So we're going to start off with a very sort of trivial observation. Let's say that you have a matrix A matrix, okay, and I'm afraid I'm going to do something that's a matrix with column vectors U1 through UN. Really, to be consistent, I should have called these A1 through AN, but in my notes, I'm afraid I've used U everywhere, so I'm going to stick with that. If the UN form an orthonormal set, then ATA equals something. A transpose A equals something. What's the something? What is that something?
Is it a diagonal matrix with the diagonal as UI squared?
The diagonals will be UI, inner product UI.
Oh.
Yeah, so the magnitude of UI squared. But they're orthonormal, so the magnitude is 1, right? So it's a diagonal matrix with ones. In other words, the identity matrix. Okay, so the proof is obvious just by just think about it. Consequence of this is that thus in solving the least squares problem, for AX equals B, one needs to solve one needs to solve this, right? One needs to solve this, right? Because when you solve the least squares problem, when you're looking for the least square solution, the problem boils down to solving the normal equations. You remember? Right? Solving the least squares problems boils down to solving the normal equations. But if your matrix has column vectors that are orthonormal, then this is the identity, right? And so the problem turns into this, right? So if your column vectors are orthonormal, then the game is very simple. right? You're looking for the x, which is just A transpose B. Okay. Okay. Everyone all right? Should I open the windows? Are you guys hot?
Yeah,
Okay, I asked them to turn down the heat, but they haven't. Okay, right. Okay, clear? So, so what does that mean? What does that mean? What does that mean? Let's think. Right. Right. The vector x hat that such that ax is closest to b, is APB, right? Right. So, right. So AX, of course, is going to be ATB. Right. And that what that says is that the projection operator onto the range of A is A transpose. Right? If you remember the least squares problem, right? The problem was that you had some range of A, and then you had some B, right? And you were looking for the P, right? You were looking for the P that was closest to B, right? And that P, which would be, this is your AX guy, also AKA P, right? What turned out to be was the perpendicular projection of B onto the plane, right? And what we've just seen is that, the P, right? P is AA transpose B, right? So what does that tell you? That AA transpose is the orthogonal projection operator onto the range of A, right? Right. So in this case, the orthogonal projection operator is easy to get, right? It's just going to be AAT, AA transpose. Okay. Everyone following? Anyone confused? Anyone confused? Close your eyes for a second. Raise a finger if you're confused. Okay, open your eyes, please.
I just have a question.
Yeah.
So, what is the orthogonal? You said the orthogonal projection.
Yeah.
Can you explain that?
Yeah. So remember, okay, so remember back when we were talking about the method of least squares. Okay, when we were talking about the method of least squares, what was the solution? The solution turned out to be that you took your B and then you split it into somebody that was in the space and somebody that was perpendicular to the space, right? We denoted, we used an S, maybe you guys remember better, like this, right? You took your B and then you split it into the part of B that is in S and the part of B that is perpendicular to S, right? And then what we showed was that that this thing was the vector in RA that was closest to B, right? That BS was the solution for that minimized P minus B, that minimized the norm of P minus B, right? If we took anybody else, then we just got bigger, right? That was the moral by the Pythagorean theorem. Okay? Okay. So, so then we said the following, that we said, okay, you've got this, here is the normal equation, right? Here's the normal equation, right? Here's the normal equation, and if this thing were invertible, then x hat was going to be ATA inverse A transpose B, right? And so what does that say? That x hat, that ATA inverse A transpose B is the projection of B onto, no, I'm sorry. Sorry. Then AX equals ATA inverse A transpose B. Right. So, so what does that tell you? That this thing on the right here, ATA inverse A transpose B, is the projection of B onto the plane RA. Is that confusing? Do you guys remember that? Anyone confused by that? Be honest.
Can you say what you just said again?
Yes, I'll say it again. Okay. So let's go back here. Let me get some space here. Okay. So right. Here's the range of A. Right. Here's the range of A. Here's your B. Right. And we're looking for right. We want x so that ax minus b is minimized. So we call method of least squares. Right. We wanted an x so that this was minimized. Right. Or to say it again, we wanted P so that we wanted a P in the range of A so that P minus B is minimized. Right? Yes? Right? That's the problem, right? We can't find AX equals B, so we're looking for x such that ax minus b is as small as possible. In other words, we're looking for some p that is a of something, right? P is going to be a of something, where p minus b, the norm of p minus b is minimized. Okay, that was the problem. Okay, you all were there, I hope. Right, and then what we saw was that this boiled down to this problem boiled down to solving, right, this the normal equations, right, and the normal equations were this: ATA x equals AT TB, right? Okay. Right. Now, right, if ATA is invertible, then we can solve the normal equations exactly, right? X is going to be ATA inverse ATB, which gives us that P, which is AX, is A ATA inverse ATB. Right? So this is the vector P that given B, this guy will be the vector P that that solves the problem. Okay. Okay. But you recall, P is actually B's, the part of B that is in RA. Right? P actually was the part of B that was in RA. Right? You took B and you split it into the part of B that was in RA and the part of B that was perpendicular to RA using the direct sum. Right? Your space Rn to be written as RA plus RA perp. Right? RA plus RA perp. And so you could take your B and split it up into these two pieces. And this P turned out by the Pythagorean theorem to be the part of B that was in RA, right? The perpendicular, which is the perpendicular projection, right, of B onto, right? So this is the projection of B onto RA. Right? You take B and you project it perpendicularly down, and that's B. Okay. So this thing here then, right? So this operator here is then the projection operator onto RA. Okay. And for us, just a second, Henry, sorry. And for us, we have A transpose A was the identity, right? Because our A's column vectors were an orthonormal set. So A transpose A is the identity, right? So for us, the projection operator onto RA is going to be A transpose, right? That's what we're saying here. The projection operator onto RA is going to be A transpose. Okay, now you can ask him.
Just why is AX is closest to B at when you like AX hat equal to AT plus B? Why? I'm just kind of.
Okay, come to office hours and we'll go over this again.
Part.
Okay. So that was basically the method of least squares. Yeah, come to office hours and we'll talk about it.
All right, sounds good.
Yeah. Yeah.
Yeah. So when we have A transpose A, so the inverse of A transpose A.
Yeah.
Can't we change that to A transpose inverse times A inverse?
A is not a square matrix.
Oh. Okay.
A is not a square matrix. Not necessarily a square matrix. So no.
So you can't distribute the inverse because it's not a square.
Because it's not square, right? You can't. It doesn't make sense to talk about the inverse of a non-square matrix.
Okay.
Yeah. ATA is no matter if your matrix is m by n, then of course A transpose is m by m. So when you take the product of A transpose against A, it'll become a square. That's square. So you can talk about it. And it makes sense to talk about an inverse, but not about the individual pieces. Okay. Okay. So, in any case, the projection operator onto the range of A is A transpose. Okay, so, okay, now think. What is A transpose B? What is A transpose B? If you think about it, like this, A transpose B. Okay? Not A transpose B, but A transpose B. Okay? Right. It's A transpose B. Well, what's A transpose B? When we get A transpose B, we're going to get a vector, right? We're going to get a vector, and right, the columns of A are the U's, right? We've transposed them, so now it's the rows of A transpose are the U's, right? What are the entries of A transpose B? This will be A times some vector, where the entries, what's the first entry? It'll be U1 against B, right? So we have U2 against B, UN against B, right? Okay, but remember the columns of A are the U's, right? The columns of A are the U's, and we're taking that matrix against this thing, and so what we get is going to be a linear combination of the columns, right? We're going to get a linear combination of the columns where these are the coefficients of that linear combination, right? So we're going to get a linear combination of the columns of A, right? Linear combination of the columns of A where these guys are the coefficients. What that says is that the orthogonal projection onto the range of A, you get just by taking the orthogonal projection of B onto the range of A, you get by taking combinations of the UI, where the coefficients are gotten by taking B against the UI. Okay. Or to think about it from the Fourier series point of view, if you take your sound and you take the dot product of your sound against the wave, and you take those as coefficients for your waves, and you add those guys together, then that is actually the least square solution to the problem. In other words, the Fourier series, the chopped off Fourier series, is the least squares solution, is the best least squares approximation to your sound. Okay. Say it again, right? You have an orthonormal set, right? You have an orthonormal set, and you're looking for the, I don't know if I can say it again. Let me try and say it again. You have an orthonormal set, and you're looking for the solution to the, you're looking for the solution to the least squares problem here, right? It turns out that the solution is going to be A transpose times B, right? That's the projection onto RA. Right? But what is that? If you think about it, if you actually calculate what that thing is, it turns out to be exactly this. Right? You just take your B, and then take the dot product against each column, and then take those combinations of the columns, and that turns out to be the best, the least square solution. Yeah, Teresa.
What do you mean when you say you chop off the Fourier?
So with the Fourier series, well, you have all these all these functions, right? Cosine, cosine 2x, sine 2x, etc., right? Right. And then you create a linear combination. You create this linear there's some way of recovering your function as this infinite linear combination.
Right.
Okay, but when you're trying to reconstruct sound, for example, you can't use infinitely many coefficients because
Right.
you have a limited space, right? So you chop it off at a certain frequency. You say I'm not gonna go beyond the nth wave.
Okay.
Right. So yeah, so that will be. So what's this? This is going to be the projection on the span of the first 2n plus 1 vectors in this first 2n plus 1 elements in this set. Yeah, Elena.
Can you explain how, when you have A times, when you rewrote A transpose B,
Yeah.
from there to the sum?
Yeah, sure. So this is that same fact we've used again and again in this course, that if you have A times C1, C2, blah, 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 through Cn, then this is going to be C1 times the first column plus C2 times the second column plus Cn times the nth column.
Oh, and in A the columns are...
Yeah, so I'm afraid A is in, because the columns I've written as U's here.
Okay.
Yeah, but that's all that is. Okay. Okay. So yeah, what does it say? That the answer to the least squares problem, if your vector has orthonormal, if your matrix has orthonormal columns, right, is going to be exactly this thing here, right? Where you just take your vector, you dot it against the columns, and then you take combinations of the columns. I'm gonna say the whole thing over in a slightly different way, and maybe that way will stick. Okay. So another perspective. Okay. So again. Again, say the columns again. Say the columns. Say the columns of A are U1 through UN, and orthonormal set in Rm. So it's an m by n matrix, and say that B is in Rm, right? Okay. Then, of course, the range of A is the same thing as the span of these UIs. Oops, UN. And let's consider this vector p, which we create as dot product of b against ui from I equals 1 to n. Right. If you think about what this thing is, let's think like this. Here is, say, 1, 0, 0, and this one is 0, 1, 0, and this guy is 0, 0, 1. Okay, that guy's 0, 0, 1, and you have some vector b. Okay, right. Then b dot the first guy, right? B is going to be b1, b2, b3. What's b dot the first guy? b1, right? B dot the first guy is b1. B dot the second guy is b2. And I'm going to stop there. You thought I was going to say b dot the third guy. Okay. Now, you say well, look, b dot the first guy times the first guy plus b dot the second guy times the second guy. What is that? Well, that's b1 plus b2, which is b1, b2, 0. Right? In other words, that is the projection of b onto the xy plane. Right? That's, you take your b1, b2, b3, and you drop it perpendicularly down onto the xy plane, and that's what you get, right? When you take this sort of thing, right? And that's because this is an orthonormal set. Okay. So this thing that we're looking at, you should suspect very strongly that this is intuitively P is the projection of B onto RA. Just from your three-dimensional intuition. Okay, so let's check it. Let's consider B minus P. Let's consider B minus P. It should be in RA perp. Right? For P to be the projection, right? For P to be the projection onto RA, well then B minus P should be in RA perp. Anyway.
So we don't do U3 because it's not in range?
Yeah.
Okay.
So I'm using U1, U2. U1, U2 is my set.
Mm-hmm.
There is a U3, but I'm not going to use it.
Mm-hmm.
Okay. So let's consider this thing, and I'm saying that that's going to be in RA perp, right? Well, let's check. Is B minus P perpendicular to UJ, right? For the J equals 1 to N. And you just do the calculations. Okay, let's look at it. Let's take UJ dotted against B minus P, right? P was this thing. B UI. you see what happens, right? What happens? We break it up, we're going to get UJB, and then minus UJ against the sum. I can pull the sum out. I'll leave it in for a second. Okay. I can pull the sum and the coefficients out, right, by linearity. Right, so this is going to be minus summation b I from 1 to n, b comma ui, and then uj comma ui. Right? Well, as I goes from 1 to n, what happens? What am I going to get here? For the most part. ui dot against uj, these are
0.
0. For the most part, it's 0, except when I equals j, right? So this is the only thing I'm going to get is I'm going to get 1 when I equals j, and otherwise nothing. So this is going to be b uj. So I get uj and b. I get b uj minus b uj. Okay. So what does that say? Thus, right, b minus p is in RA perp. In other words, p is the projection of b onto RA. Right? P is the projection of b onto the RA space. Right? Because when I subtracted it off, I got something in RA perp. Right? So P is the projection